Hello again. This is Math 2231 remote delivery for April 16th, 2020, and we will discuss part of the fundamental theorem of calculus in this delivery. Please use keys like this to perfect. Last time we talked about the definition of the definite integral as the limit of some Riemann sums, and we also developed a half a dozen properties. Here we'll talk about some more properties. Some of these are equations, but very importantly, some of these are inequalities. So this property says if I'm integrating a constant over a finite interval, that's the same thing as the constant times the length of the interval. I often use this to simplify calculations, and so I encourage you to embrace this. And you can figure this out just from drawing a picture, and this is an area of the rectangle formula will get you this result. If f is bigger than or equal to 0, then the area under the curve from A to B is bigger than or equal to 0. Here, if we really were to talk about a capital F equal lowercase f minus g, you could prove this one, but it says if f of x is bigger than or equal to g of x, then the integral of f of x dx is bigger than or equal to the integral of g of x, and I should have been saying definite integrals there. If f of x is between two numbers, a min and a max perhaps, between a and b, then the integral from a to b of f of x dx is between this from part 1 and this from part 2. I guess this is 9 and 7, I guess. 9 and 7 we can use to conclude this. And last but not least, since the absolute value of f of x is bigger than f of x, then the absolute value of the integral from a to b of f of x dx is less than or equal to the integral from a to b of the absolute value of f of x dx. Now, we should talk about some interpretations of the definite integral before we move on. We have talked extensively about this being the net area between the graph of f of x and the x-axis. Sometimes in a physics context, it is talked about calling this the net change theorem, and that is that the definite integral of a rate of change. So if you take the integral of a rate of change, you'll get the net change in the quantity. This is exactly what you did in that critical thinking exercise that we just finished, because I had you integrating the velocity. So as an example, the integral from t1 to t2 of the velocity is the change in displacement, the net change in displacement. And again, continuing, note in this case if v is both positive and negative, as it was in our example, the object is moving both to the left and the right, this will not give the total distance traveled. It will only give the net displacement. To get the total distance traveled by an object, you'd have to compute the integral from t1 to t2 of the absolute value of v of t. And it's important to note here that the net change theorem only really makes sense if we're integrating the derivative of a function. So now we come to part of the fundamental theorem of calculus, and so I'm going to call this one part 1. It says if f of x is continuous on AB, and if we define g of x to be equal to the integral from a to x of f of t dt. Now note, g of x, the x is going up here, the x is becoming the upper limit in the integral, and a is a constant. But if this is a continuous function on AB, and when they say, we're saying not if, it is. So if f is continuous, then this g of x is continuous on AB. We have to show that, and that's as a function of x. And moreover, it's differentiable on AB, and if you take the derivative of this function, you get f evaluated at x. It's important to make a distinction between the x's and the t's here. This said a little more succinctly is if I take the derivative with respect to x of the definite integral from a to x of f of t dt, I get f of x. Here is a proof of this, and the proof is what we're going to do is we're going to actually take the derivative of this using the definition of the derivative. So that means it's good review to go through the proof. So suppose that this is true, then g of x plus h minus g of x is just equal to this. Again, I'm using exactly the definitions of g in that case. But by one of the properties that we learned, I can pick an intermediate point, for example x, and I can change this thing that I'm pointing at into this. And that means that this term will cancel with this term. I'm just left with this term. Then we're going to divide by h, and you see we're starting to make this look like the derivative now. We get this expression. Now we know f of x is continuous because of the hypothesis that we have. So by the extreme value theorem that we studied and learned how to apply, we know that there are numbers c and d where it achieves its minimum and where it achieves its maximum, c and d. So that means that this expression, which is also equal to this expression, if I multiply both sides by h, I have this, and for f of c. And I will divide now by h, like I was talking about doing, and I can get that g, the difference quotient of g, is between this number and this number. Now we're going to use the squeeze theorem, because you see c and d were chosen in x and x plus h, and so that means that the limit of both of them is f of x, because f is a continuous function. That means we can use the squeeze theorem. This limit and this limit both are f of x, so that means the limit in the middle is f of x. So what we have shown is that g prime of x is f of x. So we know that g of x is differentiable on the open interval. And we also know if it's differentiable, it's continuous. We do have to be a little bit careful about the endpoints, and I don't want to dwell on that, but this is a technical math issue that gets resolved fine. So we have proven the theorem. Let's do some examples of this then. So I'm going to ask you to pause and do these two problems. Think about them, and we'll return and see how you did. Let's see how you did. The first one is a pretty straightforward application. A is minus 4, that's fine. You take the derivative, you just substitute x into the integrand, and that's all there is to it. The second one is more involved. We're taking the derivative of this, but you see the theorem only had this at the top, the function of x, and so I'm going to use the property where I change the order of the integration and make that a minus, and I pull the minus through the derivative sign. But the next thing to notice is that the fundamental theorem of calculus, as we've talked about, requires an x in the upper limit of x integration, so we got x squared. So to do this derivative, we're going to need a chain rule, and we're going to let u be x squared, and we're going to use the chain rule. So think about this as going from x to x squared and then x squared to this integral. Doing that, we'll use the chain rule, and so we'll take the derivative with respect to u. We will get this, and then du dx is going to be 2x. But then we will replace u by x squared, and we will get this as our final answer. You may want to ponder this just a little bit. And we can use the chain rule as we did in the last example to derive some more general formulas. So, you know, we talked about what happens if you have a limit in the top, a function of x, and if you have something in the bottom as f of x. And so we can talk about what happens if you have functions of x in both, and if you follow this logic, this is the formula. So the derivative of this with respect to x is, it follows this formula. Why don't you apply that formula to this, and you're to take the derivative of this expression. Let's see how you did. All right, when you simplify this, you should have gotten minus 1/2 the square root of x times the sine of 1 plus x and plus 27x squared sine of, and this is 1 plus 9x squared. Okay, so to be continued. I hope to post the next part today. Stay tuned.